get started. We are going to do today, if I can hit the right buttons, some new shortcuts. And that's not the one I want. Let's try this again. We're going to do some new shortcuts. And they are going to be the product and the quotient rule. And the names kind of tell you what they're for. We're going to use the product rule when we want to find a short way of getting the derivative of a function that's really made of two things multiplied together. And let's show you what that rule looks like. Here it is. So if you have a function y equals f of x, g of x, things like, x cubed e to the x or whatever, right? Two distinct things multiplied together. Then the shortcut called the product rule says its derivative is f dash g plus f of g dash. There's an elegance about that that just kind of looks right, doesn't it? It's got a lot of symmetry. So that's basically what you do. You multiply these two together plus these two together, and that will get you the derivative of f times g. And the quotient rule, quotient's an old name for the fraction, you've got f of x over g of x, right? So this time the function that you want to do is a fraction, f on the top and a g of x on the bottom. And the derivative for that one is less obvious, not as pretty, but this is called the quotient rule. And that's what we're going to be looking at. We're going to be looking at getting lots of practice. I hope we have time for it, for products, for quotients. Multiple derivatives just means find second, third derivative. We know how to do those. Equations of tangent lines, same basic idea. You're going to get a function, maybe one like this or this, and you're going to find the equation of a tangent line. And then we're going to finish with non-standard derivatives. These are ones that don't quite fit into these categories directly, or that there's other ways to get the answer instead of using these rules. And then we've got some special puzzle problems, situations at the end. So that's kind of today's list of items that we're going to do. So let me jump straight into a product rule. Suppose we have a function y equals x squared plus 1 times 2x take away 3. Now I could get the derivative of that by just foiling these out and then using the power rule. I mean, definitely doable, but I'm not going to. What I'm going to do is identify that this is f of x and this is g of x. And I'm going to use the product rule, which is f dash g plus f of g dashed. And just like yesterday, we got to remember that when we finish the derivative, we're not finished the question. We still have style points, right? We still have to simplify it, make it look as pretty as possible. So let's see what we get. If you differentiate 2x squared plus 1, you get 2x, and then you leave the other guy alone. That's this one. Then you leave the first guy alone, and you differentiate the second guy. And that's the derivative finished. What's going to happen now is we're going to try and make it look pretty. Distribute, you get 4x squared, take away 6x, plus 2x squared plus 2. Collect like terms, 6x squared minus 3x plus 1. Oh, sorry, plus 2. I don't know where that came from. I apologize. I think I'm thinking what's going to happen in the next line. Okay, just double check I did this right. 6x squared minus 6x plus 2. Okay, everything looks good so far, right? Is there anything you can do to make this a little bit prettier?
I guess in order to make it look like the original, we would have to foil it.
If it was possible, you're quite right. Sometimes it is doable, sometimes it's not. Let's assume right now it might be, but it might not. Is there anything that we can do for sure based on the 6, and the 2 here?
Pull the 2 out.
I'd pull it out. And that gets me 3x squared. Take away 3x plus 1. And just like you said, Matthew, what we should do now is factor that. I'm doing a quick scan through my brain, and the answer is I can't factor it, so we're finished. But, 50% of the time, roughly, you'll get a quadratic or something that is factorable, and you should do it. Right. So that's the best I can do. We'll call it good. Now, f of x and g of x are just labels for the first guy and the second guy. So you will get a question that will look like this. F of x is equal to x cubed e to the x. We will still call this guy f of x, and we will still call this guy g of x. And we will just have to think of this f is not the same as that f, right? I don't think that's a biggie. So the derivative of the function is f dashed g plus f of g dashed. So this guy just means the derivative of the whole thing. These guys mean him. You comfortable with that? You just have to have a little bit of imagination. So you differentiate this guy, you get 3x squared, leave the other guy alone. You leave this guy alone, and you differentiate e to the x, and you get that. And we are finished with calculus, and now we are on to style points. Is there anything you can do with that situation that we have in front of us? Anything you can do to simplify that, factor it, for instance.
I guess
Pull out the
remove
e
e
to
of
the
x.
I agree. Anything else? Okay, again. Definitely e to x. Anything a little bit more than just e to the
I guess
x?
e to x and x squared.
Okay. And if you do that, you're going to be left with 3 plus an x. And that would be the finish. Now, there are lots of reasons I've argued why in the past. Here's a new reason for why this is a good way of writing the answer instead of that one. One of the most common things that you're going to do once you've found a derivative is you're going to be interested in when the derivative is 0, because that tends to be, doesn't it, the toppy hills and the bottoms of valleys, right? And these are quite useful places to know about. When this function is factored, I can look at this and I can tell you that when x is 0 and when x is -3, this derivative will be 0. So I could tell just by the form that I've written the derivative, I can tell you almost immediately that when x is 0 and when x is -3, the derivative is going to be 0, and therefore there's probably a hill or a valley at x equals 0 and a hill or a valley at x equals -3. That's one of the many advantages of writing things down in their style point format. Now let's make life a little bit trickier. And this is a version of question 4. And we've got functions called g of x this time. And it's made up of this guy times another e to the x. This is going to be my f. And this is going to be my g. So the derivative of all of this is going to be f dashed g plus f g dashed. And we're going to hit a problem, aren't we? I need to differentiate x plus 5 square root of x. For differentiation, that is not really very helpful. Wouldn't that be a better way to write 5 square root of x as 5x to the half, right? So I want to differentiate you. I'm going to get 1, and then I'm going to have to do the power rule. Multiply by the power reduce the power by 1, and then leave that guy alone, plus leave this guy alone, and differentiate e to the x is e to the x. Would you agree that's a much uglier looking answer? But, you know, you get what you get. Any suggestions about how to make this look pretty? How to simplify it? You've got these two plus these two multiplied. What could I do? Do you see anything that they may share as a common factor, for instance?
Take out the e to the x.
Okay. Now, sometimes you can do a lot. Sometimes you can't do that much. Sometimes you can't do anything. But in this case, at least I did that. Do you think I should leave these two guys in the form that they are right now? Or should I change them into something else?
Change them.
Okay. Well, I don't want to have to rewrite too much here. Is it okay if I just do that in one go and you're comfortable about how I got what I got? Are you okay with that? That this guy is it? And I'm looking at that and I'm saying, huh, that's it. That's as good as I can do it. I'm just going to have to live with that. Any questions? Are we good then? I'm assuming that we are. See some faces. Can't see any of you. Why can't I can see you now? There we go. Right, we're looking good. Okay, I'm going to show you a question that isn't a trick question. It's not a trick question, but it is a question that can be done in two ways. The first way is the obvious way, which is it's just a product rule like all the others. And this is going to be called F, and this piece here is going to be called G. And we're going to get the derivative, and I'm going to do something I typically do here. I'm going to write the product rule like that. Now, have you noticed that I've missed out all the x's, right? It's not f dash to x and g of x. But can you pretend that that says f dash to x and that says g of x? It may be not a big thing, but if you're doing lots of them, doesn't it get really boring if you have to put all those x's in all over the place, right? So that's just a condensed version of that, okay? Are you comfortable with that? I don't think it's a big deal. Right. So, normal product rule, differentiate this guy, you get 4w cubed plus 6w squared. Leave that guy alone. Plus, leave that guy alone. And hopefully I've got enough room to squeeze this in. Differentiate that guy. -3w to -4 plus 5w to -6. God, that was crushed. I'll move over here, I think. So I've got this ugly pair plus this equally ugly pair. And what I need to do is style points. And this is going to be really ugly and really long, but I'm doing it anyway. Foil it. That guy times that guy gets you 4. That guy times that guy gets you -4 to the power of -2. That guy times that guy gets you 6w to -1. And that guy times that guy gets you -6w to -3. Foil these guys out. That guy times that guy gets you -3. That guy times that guy gets you 5w to -2. That one times that gets you -6. w to negative 1, and I run out of room, so that guy times that guy gets you plus 10 w to negative 3. Okay, what have I got? I got a 4 here, and I get a negative 3 here, so they get you 1. I have got this guy and this guy, so that gets me cancel. Oh, they cancel it, that's fine. I got this fella and this fella, which gives me negative 4, that gets me positive 1. And then I have this guy and this guy, who gets me positive 4 w to negative 3. And since the original question had negative powers, isn't that okay to leave this as negative powers? Would you agree that was quite an ugly question to do? It wasn't a hard question, just an ugly question. And nothing wrong with that method, and if you're comfortable with it, by all means do it. But you're going to have a whole lot of foiling to do. So I'm going to rewrite that question. And I'm going to see if there's a different approach to finding its derivative. I even make up names for things. I have a name for this situation. And the name I use, or the term I use, is just because you can doesn't mean you should rule. That's what I call it. Just because you can doesn't mean you should rule. So can I use the product rule? Yes, I can. Just did it. But just because I can do it doesn't necessarily mean that I should do it. Has someone got a different thought of how to approach the same question?
Couldn't we just FOIL it out like normal?
Yeah, at least I'm only foiling once. Would you agree? Because here didn't have to foil twice and then do a whole load of collecting. So I am not doing any calculus right now. I am just foiling. That guy times that guy is w to negative 1. That guy times, sorry, that's plus 1. That guy times that guy is w to negative 1. Let me rewrite that again. 1 negative 1. That's better. Right, that guy times that guy gets you the number 2. And that guy times that guy gets you negative 2 w to negative 2. Okay. Now, I can differentiate. And I get a 1. I get a... Oh, one of my two answers is wrong. That'll be interesting to find out which one it was. I know, I'm right. Same answer. Would you agree that's less work than this one? So sometimes you might want to try a different approach. You might look at someone and say, you know, if I just foiled that out, it would be much easier to differentiate. As I say, just because I can doesn't mean I should draw. And it's interesting going on. Yeah, let's try this one. Y is going to equal e to the p plus p square root of p. Now, I know I'm going to differentiate this. It's just going to be a normal product rule. But this term here is really not in a form that's going to make differentiation easy or even doable. What power of p, what fractional power of p is p times the square root of p? So it'd be p times p to the half. What fractional power would that be?
3/2.
Correct. If you're going to differentiate something, don't you want it to look like this guy? You agree? If you're going to differentiate it, you want it to look like this guy. Leaving it like that guy is just not going to be a good idea. So this is going to be F, this is going to be G, and we have our F dash G plus F of G dash, our product rule. Differentiate e to the p, you get e to the p, leave the second term alone. Plus, leave this guy alone and differentiate this, and you will get 1 plus 3 upon 2 p to the half. Now, I want to make life nice, simple, whatever. What I noticed here is they both have a common factor of e to p. I'll call this guy p. I'll call this guy p square root of p again. I'll have a 1, and this guy here is that guy. Not the prettiest answer in the world, but that's the best I can do. Now, I could have, and I'm not going to, but I could have multiplied this out. And it would have looked something like that red guy. Now, if I wanted to differentiate that, wouldn't I have to do a product rule and another even weirder product rule? Would you agree in this case that would be more work than leaving it alone? So sometimes leaving it alone is the right, most efficient strategy. Sometimes multiplying them out is a more efficient strategy. You'll be able to, I hope, tell when you should do it and when you shouldn't, essentially based on just experience, Yeah, I can tell that's ugly. I can tell I can live with that. So how about this question? It's a version in it. As functions go, that's one of the simplest looking things, isn't it, to differentiate? So we'll call this F, we'll call this G, and we'll get its derivative. Differentiate this guy, you get 5x to the 4th times e to the x. Leave this guy alone, and you get that. Right, let's make it look pretty. Any common factors going on here?
Pull out e to the x and x to the 4th.
We'll do that. Comfortable with that? Now let's suppose I asked you to do a second derivative. And your first thing should be, whoa, the quotient, the product rule only works for 2 guys. And we have 1, 2, 3 guys. So I'm going to call this fella F, I'm going to call this fella G, we're going to call this guy H, right? 3 different things multiplied. And now I'm looking for a volunteer.
So wouldn't it be easier just to redistribute the x to the power 4 back in and then just do it that way?
Oh, so basically I have 2 guys?
Uh-huh.
Yeah, that would work. Not only that. And when you have to do a product rule and then another product rule and then foil some things out and then, yeah, it would work. And there'd be nothing wrong with that, it would work. But I want someone to tell me how to expand the product rule for 3 things instead of 2 things. And you're just doing it by what you think it should be. Because nobody's told you what the thing is. But you should be able to think, well, isn't math got a lot of symmetry to it? It shouldn't be a weird looking thing. Shouldn't it kind of sort of look like that, but just be a bit different? Any takers?
So you do f prime of g h plus f g prime h plus f g h prime.
You nailed it. Have you ever seen that, or was that just what your brain told you?
I took calculus in high school, so I kind of have that memory.
Okay, so it's a remember. But when you look at it, is it kind of cool? I mean, not that you're ever going to do it, but couldn't you do it for 4 functions? You know, F, G, H, K. Couldn't you do a product rule for 4 functions? Now, if you do it this way, you're going to also get the answer. The way Matthew said was totally fine, right? Product rule, do your answer. But since I've got this set up, let's do it now. So you differentiate this guy, you get 4x cubed. You get an e to the x and a 5 plus x. Then you leave this guy alone. You differentiate the middle guy, which is just him, and you get 5 plus x. And then you leave this guy alone, and then you differentiate by that. So you get an x to the 4, e to the x essentially times 1. Now there are 3 distinct pieces. Each of them has an e to the x in it, so that's going to be a common factor. They all have powers of x, but that one has an x cubed, that one has an x to the 4, and that has an x to the 4, which means I can only pull out an x cubed. Okay, so what have I got left? I've got a 4 and a 5 plus x, so that's 20 plus 4x. I got 5 plus x. Yeah, a 5 plus x and an x, so that's going to get me 5x plus x squared, and this guy here is going to get me an x. Hopefully I did that right. So you're going to get an x squared. Looks like you're going to get a 10x plus 20. And we're finished. Barring accidents in counting. Are we good? Now that I've seen this, what do you think, Matthew? Do you think 2 product rules added together might be even less work than this?
No.
No. Okay.
I think it'll be similar.
Okay.
It seems quicker to me.
And when you have 2 directions to go and both work, shouldn't the answer be the one I like doing? Right? I like doing it that way. Do it that way. Nothing wrong with it. So we're now going to move on to quotient rules. So basically, quotient rule is a shortcut that allows us to find the derivative of some really messy fractions that we couldn't do any other way. So for instance, until today, if I asked you to differentiate that, wouldn't the answer be I can't do it? Right? Yesterday's power rule does not work with that guy. Now, if I switch places, I could do that one, couldn't I? I could split it into fractions and do it. But when you stick it that way around, the answer is we're stuck. So aren't you glad that somebody figured out a shortcut for fractions called the quotient rule? So the top is called f and the bottom is called g. And you want the derivative. It's f dash g, take away f of g dashed, all over g squared. Now you do the derivative of that guy, you get 2x, you leave the bottom alone. Take away, you leave the top alone, and you differentiate the bottom, and the whole thing becomes x cubed plus 1 squared. And that's calculus finished. What we're going to do now is try and make it look pretty, or prettier. I think it's probably easier just to distribute this first and then worry about common factors. So I have 2x to the 4 plus 2x, take away 3x to the 4. Double check that. 2x to the 4, 2x, take away 3x to the 4. and that guy kind of cancel out. And what have I got? 2x take away x to the 4. Okay, that's me collected like terms. Not a lot I can do here, but I can pull out a common factor of x, so I should do that. Are you comfortable with that? Okay, quotient rule. That's a little bit longer, isn't it? You got a little bit more to do. Tidying up, making it look pretty, might take a while. Try question 12. We have y equals 9x over e to the x. So this is going to be called f. This guy's going to be called g. And so the derivative is going to be f dash g take away f of g dashed all over g squared. Differentiate the top, you get 9, leave the bottom alone. Take away, leave the top alone, differentiate the bottom. All over e to the x squared. So far, so good. Right, not a lot, but we should try and make it look pretty. Agreed? Anything that you can do on the numerator, any common factors?
9 at EX.
And that leaves me with that guy. And on the bottom, I got this guy. Kind of nice when this happens. I wish it would happen more often. Can you see that I can do a bit of a cancel? Can I cancel this e to the x with one of those? And what I'm now left with is 9, 1 minus x over a single e to the x. You comfortable with that? As I say, I'd like that to happen a lot. It doesn't, but when it does happen, you should do it. Any issues? In a lot of ways, isn't this a plug and chug formula? Right, you plug in an f dash here, you plug in a g there, you muck about with them, right? Foil them, cancel them, make them look pretty. Let's do a basic fraction, which is 14 as an example of that. That fella over this fella. So the top is f, the bottom is g, and the derivative is f dash g take away f of g dashed all over g squared. Differentiate 8 minus 9t just gets you the number -9. We'll leave the bottom alone. Leave the top alone. Times the derivative of the bottom, which is just 6. All over 6t plus 7 squared. Now style points. I think in this situation, it's probably best just to distribute these and then collect like terms. See what happens after that. -9 times that is -54t. -9 times that is -63. I guess the 6 at the front would make this a little bit easier to see. So it's -6 times 8 is -48. And -6 times -9 is plus 54t. And that gets killed off by that. And it looks like we're just going to have a number left, 111. Okay. If you plugged it into Desmos, you would get some, well, it would probably look something like this. Be a pretty boring curve, and it'd have a vertical asymptote, right? What this derivative is telling me is there is no place on this curve where the derivative is going to be 0, because for a fraction to be 0, doesn't the top have to be 0? And the numerator here is a number, right? Negative 111. So I might not know an awful lot about this curve, but what I can tell you for sure is it's never going to look like that at any point on its curve, because that would give you 0 derivatives, wouldn't it? So even although it's not a lot, you can tell straight off by looking at the derivative whether or not something's likely to have a hill or a valley on it. Where shall we go next? Let's try this one because it looks weird. Capital F of x is 1 over 5x cubed. Take away 6x squared plus 9. And the top and the bottom. Definitely a fraction. I know there's only a 1 in the top, but it's still a fraction. So it's going to be f dash g, take away f of g dashed, all over g squared. F dashed is the derivative of the numerator. What's the derivative of the number 1?
The derivative of 1
Yeah,
should be 0.
yeah. So, don't know if that is weird or not, but that's what it is. So nothing times this guy. Take away 1 times the derivative of this guy, which is what? 15x squared. Take away 12x. That gets you nothing. And on the bottom, I have this guy squared. Now, 0 times anything is 0, so that expression really is gone. And if you multiply this through by -1, you get negative 15x squared plus 12x all over that guy squared. Can I do anything to this fraction to make it look prettier?
3x.
3x.
So it's going to leave me with negative 5x plus 4. And that is totally acceptable as an answer. It just looks ugly to me. There is no need for you to do what I'm just doing. Just doesn't that just look prettier? I know it's not. It isn't. You know, there's nobody in the world's going to say, "Oh, you didn't do that," because that is totally acceptable, right? But some things just bug me, and that's a situation. I don't like math things to look clunky, I guess. But that's what I would have done. And I'm pretty sure WebAssign would understand both those answers, so you'd be fine. Any questions? Quotient rule going the way you thought it might, right? Here's a formula, plug and chug, make it look pretty. Just picking ones as they turn up. And this is a version of 18. The reason I'm choosing this one is because of the square root of x's. In particular, I hope you realize that you have to rewrite it for differentiation purposes like that. Would you agree? You have to do it that way if you're going to differentiate. So the top is F, the bottom is G. We are good to go now. F dash G, take away F of G dashed over G squared. If people do not like magic, because I've just said, look, this is how you get the derivative with a product. This is how you get derivative with a quotient. You can actually go and look up videos of people proving it to you. So if you're interested, I would do a search, something like the proof of the product rule or the proof of the quotient rule, and you could get to see why this works. Okay, I'm going to differentiate the top. That's 1/2 x to the negative 1/2, and then I'm going to leave the bottom untouched. Right. Take away, leave the top untouched, and differentiate that guy. And so you get 1/2 x to the negative 1/2. Derivative of that guy is 0, so you don't have anything. And the whole thing is going to be that guy squared. And in this situation here, I think it would be easier to just, distribute things and then collect like terms and see what happens. So I have to write this down on a piece of paper, because I think if I say it, it won't be clear. This guy times this guy is 1/2 to the negative 1/2 times x to the positive 1/2. What do you get when you do that guy times that guy? What's that equal to?
1/2.
So you get 1/2. And then this guy times this guy just gets you 5x, 5 over 2x to the negative 1/2. And this guy times this guy gets you negative, well, let's put it in. If I do negative x to the 1/2 times 1/2 x to the negative 1/2, don't these two essentially cancel out? And are you okay with the answer being negative 1/2? Are you comfortable with that? Okay, so we now have just one term left on the numerator and one term squared on the denominator. We want style points. We want to make this look like the original. We also want to make sure that it's written in the best way possible. I do not like that negative 1/2. Would you agree that negative 1/2 is not pretty? I would like it to be somewhere else and not negative anymore. Are you comfortable with this happening? You comfortable with the 2 coming downstairs and this becoming positive downstairs? Okay. Now, all I'm going to do now is make it look like the original. We're comfortable with that guy? As good as it's going to get. Okay, let's try this fella. A, B, C, and D here are all considered constants, right? They're all considered just numbers. So treat them like 42, right? Just treat them like a number. So to find the derivative, that's going to be F. This is going to be G. Quotient rule. f dash g, take away f of g dashed all over g squared. What do you get if you differentiate ax plus b with respect to x? What do you get? What's the answer?
Just A.
Just A. If it said 5x plus 7, wouldn't you say 5? If I said 20x plus 1,000,000, wouldn't you just say 20, right? Ax plus b. The b is a number, so its derivative is 0. And isn't the derivative of ax a? So A. Leave the other one alone. Plus, leave the top alone. That's f. And if you differentiate cx plus d, you comfortably you'd get c. And I don't know where that came from. It should be minus. And now, all over cx plus d squared. And I'm going to distribute each term. So I went a times those two guys and take away c times those two guys. And quite nice. They kill each other off. And you are left with an AD take away a BC all over CX plus D squared. Quite a nice answer. It could have been a lot uglier. Any questions? Good. More plug and chug, maybe just a little bit more awkward, but essentially plug and chug. Let's move on then to multiple derivatives. We've actually done one of them. The one I'm going to start but not finish is one similar to the homework question 21. And the reason I'm not going to do all of it is because it's ugly. At least that's what I think it's going to be. Well, we're being asked to find the first and second derivative. So that's what I mean by multiple derivatives, right? First derivative, second derivative, third derivative. So they might, in a different world, ask you that as well. So it's going to be f dash g, take away f of g dashed all over g squared. There is nothing that weird about the first derivative, right? It's a pretty bog standard quotient rule. Differentiate this guy, you get 1. Leave that guy alone. Take away that guy times the derivative of this guy, which is 2x, all over x squared minus 4 squared. So that gets me an x squared take away 4, take away 2x squared, all over this guy. And there's nothing pretty about the answer. But that is the answer. I know they cannot cancel. I mean, I guess I could pull out a -1 as a common factor. I don't think it would help at all. So I'm just leaving it like that. Now, to get the second derivative, you're going to call that guy f, and you're going to call this guy g, and you're going to go through that same process. This is a place where I'm going to be stopping because this is ugly. There's no way in the world I'm going to leave g like that, because don't I have to differentiate g? And if I leave it like that, I've got a problem. So has anybody got suggestions for what I should do about that term to make it differentiable?
Can you cancel out the numerator with the denominator?
Say again?
You can cancel out the numerator with the denominator because it's x squared minus 4, and the denominator is
No, Unfortunately, you can't because it's a negative x squared minus 4, not an x squared minus 4.
Okay.
Right. So what could you do with this instead? Since that's not possible, how are we going to work around this issue?
Factor out.
Yeah. Can you just trust me that it ends up being that? So if it's okay to differentiate, the bottom has to be turned into this. And it's just going to grow into this big ugly fraction that will simplify a little bit, and then you try and make it look pretty at the end. It is what it is. Not very pretty. So I should start chalking off my list. We've done products, we've done quotients. I know there's not many, but we have done one, at least partly, for this. The next one is a question that we have done before, but we'll do one just to show you. And that is finding the equation of a tangent line. So what I'm doing is a version of question 22. The curve, the function that we're going to find the equation of the tangent line to is that guy. And we're going to do it at the point 0, 1/4. Its derivative is going to be a quotient rule. Nothing too surprising yet. Differentiate the top, you get 1. Leave the bottom alone. Take away, leave the top. And if you differentiate that guy, you get e to the x. And the whole thing's going to be that guy squared. I'll distribute these and see what happens. 1 times 3 and 1 times e to the x. Take away an e to the x. Take away an x e to the x. Those cancel out. So I am looking at that guy. Now, since I want to find the equation of the tangent line, I need to know what the slope is, and it's going to be at x equals 0. So the slope of the tangent line is going to be the value of the derivative at 0. So it's 3 take away 0 e to the 0 over 3 plus e to the 0 squared. Well, nothing times that's nothing, so the top's 3. 3 plus 1 is 4, and 4 squared is 16. So I know the slope of the tangent line is that guy, and I know the point that the tangent line is going to pass through is that guy. So I can use the point slope equation to find the equation of the tangent line. What's that going to be? Y take away a quarter is equal to 3/16 x take away 0. And I'm running short of room here. So it's going to be 3/16 x. And so we have 3/16 x plus a quarter. Is that a pretty straightforward question? Find the equation of a tangent line. Main difference is, in this question at least, we're going to use a quotient rule. Maybe the next time you'll use a product rule. Let's check it out. We can always check things out using Desmos if it's a tangent line question. So here we go. What's it going to be? 1 plus x over 3 plus x. Okay. So y equals, I think I'll need brackets. 1 plus x divided by 3 plus, I just said x, didn't I? Yeah, good. Divided by 3 plus e to the x. Okay, so it's, I'm not sure what kind of curve it is. There it is. I'm interested at the point 0 or quarter. Okay, so looks weird. Hopefully it'll sort itself out when I do that. Okay, 0 quarter, which is here. And the tangent line that we had equation y equals 3/16 and it had, I believe, plus a quarter. Can't find it now. Yeah, plus a quarter. Oh, am I good or am I good? Would you agree that's a tangent line? Perfect fit. Look good? Yeah. You can adjust the windows if you want to see it, but normally what I do is I just zoom in. And if you zoom in far enough, don't they both blend together? And that's a good sign it's a tangent line. So we got it. And time to move on. So what is left? What are the kind of questions that we haven't covered? Well, we have non-standard derivatives. And that's just a phrase I just kind of made up to account for not everything fits nicely into the same box, right? Just some functions that you want to differentiate just look and have to be treated in some way or some form differently than others. So I'm going to go through each of these guys, and I'm just going to talk about how we would approach each situation because they're different. This is a version of 25. We're being asked to differentiate this fraction, sorry, this product. This one would qualify as a just because you can doesn't mean you should situation. Couldn't I do this guy with the product rule? I mean, he's set up like a product rule should be set up, right? This guy times that guy. Agreed? I could do it with the product rule. Can you trust me that if you did it with the product rule, you would get the right answer, but you would be fighting it all the way, right? It'd be products here and foiling there and collecting terms and a whole load of work. How else could you do it now? A different approach. How could I find the derivative of this fella?
Rewrite and foil.
Yeah, just foil the whole thing out. Will it be an ugly foil? Definitely. But once you've finished the foil, won't you just have various negative powers of u that you can differentiate relatively easily? Right? So in that case, I would suggest foil. Could you do it the other way, product rule? Of course you could. I wouldn't suggest you do it just because it's a lot of work. That's the only reason. How about this one? Actually, pretty much the same as question 25. Couldn't you just foil it out? I'll tell you the answer because it's an easy one. If you foil this out, that's what you end up with. Would you agree that's very easy to differentiate? If you left it in this form, wouldn't you have to, well, for starters, wouldn't you have to call it this? Right, and eventually you would get, well, since the derivative of this one is so easy, eventually you would get that. How about this one? It is a quotient rule. If I wanted to do it as a quotient rule, I would have to do just a minor change. I would have to write it like that. because if you're going to differentiate things, you need fractional powers, or in this case, negative powers. And if I differentiated that, it would eventually, it would work, right? You would get an answer. Is there any other approach to changing what this looks like to make it easier to differentiate? Any ideas?
The denominator change it to all to -1 power.
You mean like this?
Including the x. So the denominator will be parentheses x plus c, x to the -1 to the -1 power.
Oh, so you would, if I'm picking it up right, you would write the bottom to look like that. Is that what you're saying?
No, so the whole thing, x plus c, x to the -1, and the whole thing parentheses to the -1. So it would be x to the -1 and bracket x -1 power.
Wow, that's an interesting thought.
So it would be all to the numerator.
Wow. So something like that?
Yeah,
I
would that
wouldn't
work?
do that. Theoretically, yes, but I think it would be even worse than the quotient rule. So yes, it would work. No, I'm thinking of doing this. You know, if you multiply a fraction by a special version of 1, you remember that algebra trick? You're not changing the answer, you're just changing how it looks. Well, let's see how that comes out. Well, x times x gets you x squared. X times this guy gets you x squared, and x times this guy gets you plus c. Would you agree that function would be a lot easier to use the quotient rule on? That's it. So I'm just changing this ugly guy to something equivalent, but less ugly. That's about the best I could do. But it was interesting to see your thought process. Now, I've kind of kept this version to be the last one, because question 24 is kind of the, how would I describe it? It's like somebody just deliberately made your life hard. Look at that question. You want to differentiate it. There is no algebra to make it look prettier, right? So I'm telling you that right now. You can't like factor it in some way or multiply the top and bottom by x and it's suddenly going to become nicer. This is an example of a question where something really weird is happening. If I do the quotient rule, which is the only thing I've got, right? So I must do it. Right? It's the only way it's going to work. Watch what happens. It's going to be f dash g take away f of g dashed all over g squared. Now, when I get functions that are really ugly, I tend to do the working at the side here. And I write down who f and g are, and I also write down what the derivative of f and g is. What method shall I use to find the derivative of f?
Well, I was going to ask if on the numerator, you should be doing the product rule first,
Yeah.
and then switching into the quotient rule after that.
Right, so if you mean by that I need to do the product rule, and that I totally agree. So what you get is 3x squared e to the x plus x cubed e to the x. So essentially this question is a quotient rule, but inside that quotient rule, don't you have to do a product rule? So can you imagine that, you know, there could be some situations where the quotient and the product rule are both happening within the same question. And that would be an example of it. really ugly, really messy. No shortcuts. You just have to fight your way through. And that is the end of the non-standards. So in those situations, something's just not as normal, right? You have to do something to make it work better. Like, or there's a product rule where a quotient rule mixed together, that type of thing. So this is going to be question 28, our first one of the special situations. And we're being told that f of x is e to the x times g the x. We're being told that the value of g0 is 3, that the value of g dashed of 0 is 5, and we're being asked to find this guy, his derivative at 0. So I'm going to call this f, and I'm going to call this guy g, and so the derivative is going to be product rule, f dash g plus f g dashed. Well, if you differentiate e to the x, you get e to the x, and then you leave this guy alone, you get g of x. You leave this guy alone, you get e to the x, and you differentiate this guy, and you get g dashed of x. And now we pause, and we should be saying, hey, where do I go now? Well, this is not your typical find the derivative, writing the answers, some function of x. Have you noticed that this answer has g and g dashed of x into it? And they told us over here what the value of those are at 0. And they've also said, I'd like to find f dashed of 0. So if I make x 0, then shouldn't this be true? Does that make sense? That if f dashed of x is this, then shouldn't f dashed of 0 be this, right? All the x's are now zeros. And what do I know? E to 0 is 1, g of 0 is 3, e to the 0 is 1, g dash 0 is 5, 3 add 5 is 8. And that is the answer that we're looking for. A little bit different, a little bit unusual. That's what we got. 2 more of these. We are being told, which one? This is 29. We are being told that h of 2 is 4. The derivative h dashed of 2 is -3. And we're being asked to find a rather clunky notation. The value of the derivative with respect to x of h of x over x evaluated at x equals 2. So I'm going to start off by just calling this fraction y. And that's going to be my top guy, that's going to be my bottom guy. And I'm going to find y dashed. And that's going to be f dash g, take away f of g dashed over g squared. So I'm going to focus on this thing here, and I'm calling it y. And then I'm going to differentiate it, which is what that's telling us. So here is the guy, and this is how I'm going to find its derivative. If you differentiate the top, you get that, times the untouched bottom. Take away, leave the top alone, and derivative the bottom. All over the bottom squared. And here, they're saying evaluate this derivative at 2. So it's going to be that guy times 2, take away that guy times 1, all over 2 squared. And this fella here is what, -3. So -3 times 2, 4 times 1, all over 4. -6, take away 4 is -10. -10 over 4. Answer I get is -5/2. Any questions about that? Or the previous one for that matter? We're just dealing with derivatives, but sort of a derivatives of things we only know a bit of, right? We don't know half the thing, right? We don't know what the top is, right? Or we don't know what one of the two things that would be multiplied are equal to. So there's one last one of these, and it's going to be, I believe, question 30. And a version of question 30 says that my function g of x is x times f of x. And they tell me that the value of the function f of 4 is 5, and that f dashed of 4 is -5. And then it throws this one. This is what they're asking us to find. Find an equation of the tangent line of g of x at the point x equals 4. So in a lot of ways, this looks impossible. How can you find the equation of a tangent line to a function when you don't know what the function is precisely? Don't we only know that it's x times some guy called f of x, and they haven't told us who f of x is? Now, if I want to find the equation of a tangent line, don't I need to know its slope and the point? Let's see if we can get the slope first.
Wouldn't our slope still be -5? Or oh wait, never mind.
Oh, that's for f, but we will use it. Would you agree in this particular case that it's a product rule? And the product rule then for this particular combination is first guy times untouched second plus untouched first derivative of the second. So differentiate this guy, you get 1 times f of x plus this guy times f dashed of x. Now the slope of this particular function is the value of the derivative at 4. For the slope of my tangent line is going to be the value of this guy at 4. So it's going to be 1 times f of 4 plus 4 times f dashed of 4. And that's going to be, what, 5. So 1 times 5 plus 4 times -5. And I believe I get the answer -15. So far, so good. Now you might think we're stuck, because I now also need to know the coordinates of this function at x equals 4. Well, I know 4, agreed? But I now need to find the y coordinate at x equals 4.
Wouldn't you
How
use
do
that
I
like
get that?
you would use the original function and just input 4?
Yeah, so g of 4 would be 4 times f of 4. So g of 4 would be 4 times 5. G of 4 would be 20. There, would you agree we've got everything we need? We have a slope of -15 and the coordinates of the point is 4, 20. So what these last group of 3 or 4 questions was showing is that even if you only have imprecise information, right? You don't know everything you need for the function that you're dealing with. If you're given a little bit of extra information, you can still find values of derivatives, and you can still find equations of tangent lines. Because I can imagine situations where, you know, in reality, you only know sort of a half the story, right? You don't know everything, but you still want the answer, right? You still want to say, could I get the answer to this question, even if I only know half the things I would want to?
Oh, man.
And the answer is yes. I hope that wasn't a sigh of, that was horrible. I think that's kind of cool.
Oh, man.
It probably is. Okay, let's, where was I? Oh God, we have finished. There's everything that we need to know for our midterm, but I want to use what time we've got left to look at the next section. So the next section is going to be trig derivatives. And I want to get started on that. And tomorrow I'll do more trig derivatives. That won't be in the test, the midterm, and it won't be in the homework. But, you know, it's important that we use all the time, especially in the summer. So let's look at a new problem.
Oh,
How to
God.
find derivatives of trig functions. Well, let's start by doing a pseudo proof. So I'm going to eventually give you all the trig functions derivatives. There's 6 of them. And so here is going to be the function once we figure it out. And here is going to be the derivative. So the guy I'm going to start with is the sine of x. And this, as I said, is a pseudo proof. If I draw a bad version of the sine function, would you agree it looks something like that? Great. That's what a sine function looks like. And I am now going to do what the sketch of its derivative would look like. Now, where are we going? At this point here, and at this point here, don't we have horizontal tangent lines? And we normally drop down little invisible lines going this way, and another little invisible line going this way. And I guess I could put in some places. That's 2 pi, that's pi, that's at 1/2 pi, and that's at 3/2 pi, and that's 0. Right? So at 1/2 pi, right there, and at 3/2 pi, we know the derivative is 0. And that breaks my region into these guys, region 1, region 2, region 3. Now in region 1, would you agree the derivatives are positive? So it's up here. In region 2, aren't the tangent lines all pointing down the way? So that's negative. And in region 3, they're all positive. And there's an example of what the derivative would look like.
So then the derivative of sine x is cosine x?
Isn't that miraculous? That the derivative of the sine function is the cosine. I mean, if you agreed, it's kind of interesting that that's the truth. So cosine x. So I said I'm going to do all 6. So that's my goal for today, to try and show you the derivatives of all 6. Now, if I had time, I would draw a cosine one and do the picture of the derivative and kind of convince you, but you're just going to have to trust me. It's not quite what you wanted. It's a negative of sine x. You just trust me on that. It's upside down version of sine x. Now, there is a tan x. There is a cosecant x. There is a secant x. And lastly, there is a cotangent x. And these 6 guys are the 6 trig ratios, right, from 142. So the derivative of sine is cosine. The derivative of cosine is negative sine, because I told you it was. What I'd like to do now is pick one of these 4 guys next. So which one do you want me to find the derivative of next?
Let's go with tangent x.
Okay. So I want to find the derivative of tangent x. Now, I'm not going to do it by a picture. You could sort of do it, but I'm not sure how convincing the answer would be, and you'd find it very difficult to get it. So what I'm going to do is I'm going to rewrite the tan of x as sine x over cosine x. Would you agree that's one of the identities? Tan is sine over cosine. The advantage of doing this is that I can now do the quotient rule. And the quotient rule says that the derivative is f dash g, take away f of g dashed, all over g squared. And I know what the derivative of sine and cosine is, right? So I can do that. So let's see what we get. If you differentiate the sine, you get a cosine. Times you leave that one alone, so you get another cosine. Take away, leave the top guy alone. And if you differentiate a cosine, you get a negative sine. All over the bottom guy squared. Now, cosine times cosine gets you cos squared x. Negative sine x times another negative sine x gets you plus sine squared x. And cos x times himself is called cos squared x.
So should we end up with, because the top is an identity, right? So wouldn't
Correct.
that give us 1 over cosine square, cosine x square for tangent x?
Yeah, that makes sense. 1 over cos squared x. And now we enter style points. Well, you might think there's no style points. That's pretty nice looking. You couldn't do much to that. Well, you remember my 3 rules. Number 1, make it look like the original. Number 2 was factor the heck out of it. But number 3 is the killer. Look for identities so you can rewrite them in other ways. Now, we've already used one identity to get that top one. The next one is less obvious, but nonetheless, we use it. There is one of the rules in style points is avoid fractions whenever possible.
So would that be secant x square?
And that's the answer. You as comfortable with that guy? Now, we don't have a lot of time to show you the others, but if I was going to find the derivative of cosecant squared, I would call it 1 over sine x and do a quotient rule. If I wanted to find the derivative of secant x, I would call it 1 over cosine x and use the quotient rule. And if I wanted the cotangent x, wouldn't I just realize that it was cosine x over sine x and use the quotient rule? So you can see that's how I would have done it every time. So I'm just going to tell you what you're going to get. This guy here ends up being secant x tan x. This guy here ends up being negative cosecant x cotangent x. And this guy here ends up being, if I got that, oops, I apologize, negative cosecant x, cotangent x. And this guy here, right, this one here, he ends up being negative cosecant squared x. So, now,